We're going to begin talking about temperature now. It's one of the main variables in weather. If you walk outside, you want to know if you're going to freeze, be hot, what's it going to feel like? And that is really directly related to temperature. So maybe you want to know why the temperature changed. Yesterday it was balmy 50 degrees. Today it's 2. Why did that temperature change? Well, if you're forecasting the weather, that's definitely something we want to be able to give you. So let's learn a little about things that influence temperature. So we brought in all kind of energy into the atmosphere last week. We talked about that. Well, we want to move that energy around. Heat is the transfer that we used, or the atmosphere uses to move energy. So what is temperature? Let's define it first. Temperature is directly related to kinetic energy of atoms. Kinetic energy is energy in motion. So if the atoms were all still, there'd be no kinetic energy. But they're not. Atoms are constantly moving. It's weird. I always thought it was kind of strange to think that everything in my body or in the atmosphere, all these hardwood tables or desks, the molecules are moving. The faster they move, the hotter the temperature. The slower they move, the less the temperature. So that is what temperature is. It's motion of the atoms or molecules that make up something. So heat is energy in transit. It's energy moving from one place to another. And interestingly, heat always moves from a warmer object towards the colder object. It's trying to make the colder object warmer. The atmosphere, very first off, would love the temperature to be the same everywhere in the globe. That's what it's always working to accomplish. We just learned last week that the energy coming into the equator is way different than what's up north. That in the summertime, the energy is much different than it is in the wintertime. So we learned all of that just so we know that now all that energy, the atmosphere wants to make it the same. It's trying to move all that energy from the equator up to the poles. And by the same token, it's trying to smooth everything out. So temperature gradients are basically how close together temperature changes are. The other week, very strong cold fronts went through much of the United States. I showed you a picture in the blog this past week of the low that impacted New Orleans. If you looked at that, you'll notice the temperatures around New Orleans were in the 20s. But if you look south over the Gulf of Mexico, they were in the 70s. So there was almost a 50-degree temperature change over, maybe 300-400 miles. So that is a temperature gradient. How fast does the temperature go over a distance? How much does it change? If, for example, everything had been 70 degrees, it's a very little temperature gradient. But in this case, it was quite a lot. So the second law of thermodynamics, law 2, states that heat flows in response to that temperature gradient. So it's always going to flow towards lower temperature. So if I have a burner on the stove on, and I accidentally touch it, my hand is significantly cooler than that stove. So what is happening? The heat that was on the stove is transferring to my hand. My hand doesn't like it. It probably got burned in the process, but that heat just obeyed the second law of thermodynamics. It went from the hotter to the cooler. So what are some methods that heat flows? Radiation. We talked a lot about that last week. It still happens. Microwaves heat up your food. So that's one very quick example of heat exchange. Conduction. Conduction is where I touch something and heat changes from where I touched it or something touched something. In the summertime, black asphalt gets white hot. If you touched it with bare feet, you'd be milking pretty quickly. Hot sand in the summertime on a beach. Again, heat is being transferred from that sand to your foot. That's conduction. Convection is a little different. It only occurs in a liquid or gas. And we're going to explore that, just as we are going to explore latent heat. Latent heat comes about because water changes phase. So, we talked a lot about radiation, and we're not going to deal much with it here. Here we talk about conduction. Some things conduct heat much better than others. For example, copper conducts it very well. What is convection? So, I heat the ground. That air is becoming spread out, so it's becoming less dense. Well, the less dense something is, that air tends to rise in a liquid or gas. If you ever boil water, you see these bubbles coming up. That's convection. Transferring heat through that air or a liquid upwards. So the warm air that was at the surface is being lifted up. It cools now up at the top, and that cool air then sinks back down to the ground, making a big loop. That is convection. Sensible heating is conduction and convection together. The conduction would be taking place at the ground level probably, and the convection would be taking place throughout a layer of the atmosphere. So, latent heating. If water didn't change phase, it would make life, again, a little easier in the atmosphere. Water does. It has all three phases in the atmosphere. It's the only element that does that. It has a vapor phase. Can't see it then. Just out there in the vapor. It's always some water in the atmosphere. It can be very small amounts at times, or it can be a lot. When it condenses from that vapor phase to a liquid, you see little tiny droplets forming, like clouds. So there is condensation occurring. Now, if it keeps getting colder, temperature goes below freezing, you start getting ice, solid. So, what happened then to the energy? Well, water vapor, because the molecules are spread apart and moving quickly, has more energy in it than a liquid. So when condensation occurs, heat is released into the atmosphere. The atmosphere is warming. And believe it or not, when a liquid freezes, there's more heat released into the atmosphere. So the atmosphere is again warming some more. Yes, there are other offsetting things happening that probably remove that from happening to the atmosphere. The atmosphere is not, oh, wow, it's really warming up. It's snowing outside. No, it's not. But that does happen, and it impacts how heat moves within the atmosphere. Exactly the opposite occurs. If I go from a solid to a liquid, I need energy. I go from a liquid to a gas, I need more energy. So it takes energy from the atmosphere and pulls it in that. That is latent heating. So the oceans are big bodies of water, and they influence the climate near them, especially if the wind is coming from the ocean to the land. So on the west coast of the United States, the winds generally in mid-latitudes come from west to east. So most of the air is flowing off the Pacific Ocean and in to California, Washington State, Oregon. What happens? The ocean doesn't change temperature a lot. It takes a lot of energy to make the ocean hotter or cooler. So even here where I live, the oceans reach about 70 degrees in the summertime, may make it upper 70 sometimes. At wintertime, they usually go down into the mid-40s. So yeah, there's some temperature change here, but not the drastic change where I might be down in the teens inland here where I live, and in the close to 100 in the summertime. That is a whole lot bigger change than what's happening over the ocean. So because of that less change, the maritime influences on the Pacific Ocean to San Francisco moderate its temperature so that in the summertime it doesn't get as hot, in the wintertime it doesn't get as cold. Now, you go inland to St. Louis, what happens? You wind up with a lot hotter summer, much colder winter, because you don't have the influence of the ocean. There's also radiation comes and does all kinds of stuff. Radiation that comes in, we know can scatter. We learned it reflects. We learned it can be absorbed. Radiation that goes out from the earth may be absorbed by greenhouse gases and come back, or may be emitted into the clouds or out into the atmosphere. That may cause latent heat flux. All these things got to be accounted for if I'm figuring out the temperature. And here you can see the convection can produce cumulus clouds. Think about it. If I have a cumulus cloud, I've pulled heat from the ground up into that cloud. So I have transferred heat from the surface of the earth into the cloud. First process. Second process, in that cloud, oh yeah, I had water vapor that now has condensed and become a cloud, a liquid. Heat was released into the atmosphere, so more heat is now being poured into that upper level of the atmosphere. So I've just taken all the heat that I lifted up and enhanced it literally by developing a cloud so that we're transferring more heat from the ground to the atmosphere by this method. So when you see a cumulus cloud, you see a lot of heat being transferred from the ground up. That's why they happen in the summertime. They like that heat. And here is just showing how much of a deficit there actually is from radiation in the northern latitudes compared to down south and across the tropics. Air masses, another means of moving heat around. The other week we had, like I say, a very strong cold front went through all of the eastern United States. Before that, temperatures in many areas were in the 40s and 50s. After it went through, it went down below zero in some locations. That is an air mass change. You had a maritime tropical air mass before, even continental tropical. Continental tropical would be drier but warm. Maritime would be wet and warm. One of those type of air masses that got taken over by a polar continental polar air mass. When it did that, what happened is that cold air pulled in, came out of Canada. I showed you a map a while ago of northwest Canada and how the temperatures were in the minus 20s up in that area during the day. Think about it. The air is sitting over a large field of snow, doesn't get much energy at all from the sun during this winter time. It just gets colder. So that is the source region of these continental polar air masses. Could be continental Arctic as well. They can be called that sometimes when they come off the Arctic Ocean. So these move energy around the globe. And tropical storms and hurricanes as well. So the weather is all caused by this imbalance of these temperatures. If we didn't have that, weather might not be too hard to forecast, but we do. So that causes it. Another fact, during the daytime, in the very first questions you had to answer were, why is the max temperature in the afternoon? Not during the day, not during maximum heating at noon. Well, what happens is the sun heats, comes up, there is some amount of infrared radiation that leaves the earth, and there's definitely some ultraviolet radiation coming from the sun in. The ultraviolet is stronger at that moment than the sun, than the infrared radiation. So the temperature is going to begin to rise. As the temperature is rising, the amount of infrared radiation is increasing. But they still have more solar radiation. At some point in the mid-afternoon, they equal each other. That will be the max temperature. And now, after that, the infrared radiation is going to begin to increase more than the solar radiation. You wind up cooling. So that is your drop off and nighttime low temperatures. Soil can make a big difference in the amount of air temperature. Bare soil absorbs a lot of heat, whereas snow, like we've been having, has a very high albedo. It reflects all that sun's radiation back into space. It also allows great radiational cooling, infrared radiation to go out at night. So wind up with very cold days and nights where there's snow cover. We actually had some snow cover down in this area, which is unusual this past week. And you could see the difference where the snow was for where the snow wasn't by the high temperatures and the low temperatures. Interestingly, in soil, the bare ground, if that ground is very dry, it doesn't have any latent heat being released or used, it winds up getting very much hotter than ground that's sopping wet. If I have puddles on the ground, the first place the solar energy is going to go is to evaporation. In other words, it's taking liquid to a gas. It's absorbing your energy. So therefore, it's not going to get as hot as if it was very dry outside. And little heat island effects as well input our temperature as well. So hope you got a little bit out of this. Just gives you some ideas of how your temperature is going to change from location to location. Let me know if you have any questions this week.